This is lecture number 7. In today's lecture and then next lecture, I'm going to review three important postulates in quantum mechanics. Um, in the previous lecture, I gave a brief introduction to first and second postulate, and then today in today's lecture, I will try to go deeper and then try to interpret some of the statement. So the first postulate was that the quantum state of the given particle is is always represented by a vector in a Hilbert space. And then I will define the Hilbert space in more detail a little bit later. And one of the embarrassing part is that the quantum mechanics requires this postulate, but the law of the quantum mechanics actually doesn't tell us uh, exactly how should be the Hilbert space should be, or the what should be the um, Hamiltonian look like. So yeah, for those part, it should be actually found by experiment. And then the last 100 years or more than 100 years was spent on figuring out what is the proper state space for some given quantum system. And by now, people have much better understanding. And then and still, some of the new material might have some different quantum space. So in that case, you might have to work on more detail. But in principle, um, nowadays, most of the formula were made, and then the remaining part is whether we solve the problem or how well we can control. And then in the last lecture, I gave you a simple Hilbert space example, which was composed of 0 and 1. And then for the time being, I will also use such kind of space. Then the next question is, how is such kind of abstract vector space is implemented in terms of the real physical system? And before I talk about it, let me just um, give you a more rigorous definition of the Hilbert space. Hilbert space is generally called as inner product space, but it also requires one more requirement such that which means that complete. And then complete space, in many of the cases, you probably don't need to understand the concept of the complete space. But just in case you are wondering what the complete space means in terms of the mathematics, then we should first think about something called as a Cauchy sequence. And then, of course, a mathematical definition of a Cauchy sequence also requires additional explanation. So I will just give you some example of the Cauchy sequence, and then what do I mean by convergence sequence? So, for example, let's assume that we can imagine the sequence which is composed of 1 over n, and then we are assuming that n changes from 1 to up to infinity. Then we know that this value will gradually approach to the 0. So in other words, the limit value of 1 over n is 0. And however, depending on how we define our space, some of the space may not include a 0, because we can think about the interval which starts from not from 0, but any value above 0 is included, but 0 by itself is not included. And then the other end is goes to the infinity. So in other words, this interval can be also described by x is larger than 0. So this might be a good space, depending on your definition. However, in this kind of space, if all of these sequence, 1 over 3 or 1 over 100 or 1 over 1,000 or whatever value, they will all belong to this space. However, the limit value, which is 0, is not included. So in this case, we cannot say that this Cauchy sequence is not convergent sequence in this space. So in other words, if we want to claim some space is a complete space, then the limit value of each Cauchy sequence should be also included in that space. Yeah, another similar example you might consider is the concept of real value, and then rational value and irrational value. And then you know that the irrational we can find out a lot of sequences which exist in which belong to the um, rational rational value. However, the limit value might not belong to the rational value. So in that case, if the space is only composed of the rational numbers, then it is not a complete space. However, for the real value space, then that includes both the rational value and the irrational value. So all those rational value sequence will eventually have the limit value inside the real value. So real value space is complete space. And then for the I mentioned that in this lecture I will try to give you some idea about how this Hilbert space is implemented physically. So I will give you two simple physical example which can represent Hilbert space composed of only these two vectors. One of the simplest example of the quantum system is the hydrogen atom. All of you learned about the Bohr model of the hydrogen atom in your middle school. And when you learned about that one, one of the most embarrassing fact is that the amount of energy which can carried by the electron is not continuous. If the um, mass of m is inside the gravity field, then the height of depending on the height of this mass, then the potential energy is being changed. But the point here is that we can choose any arbitrary height here. So that, in other words, you can always um, um, uh, this mass can have any arbitrary number of the energy. On the other hand, when the electron is inside the atom, the amount of energy which can carried by the electron is not continuous. It is discrete, like as this graph shows. And then the name quantum actually comes from such kind of observation, because quantize means that quantities are discrete. And another effect you also learned is that the electron inside the atom can change their energy level. So the electron can be sitting in this energy level or another energy level, and then they can decay to some of the lower energy level. And then when the amount of energy is being changed, then that means that the total in that case, we should still maintain the energy conservation law. So to satisfy energy conservation law, the only option is that the amount of reduced energy should exist in other form. And in nature, what happens is that the different energy is being carried by photon. So whenever the electron loses its energy to some lower level, then there will be accompanying photon being emitted from the atom. So because of the photon, the energy conservation is preserved. And then the next question is, when the electron is in the lower energy, can you change the energy of this electron to higher energy level? And to do that, what you have to do is you should use the reverse operation, meaning that instead of emitting the photon, which carries the energy, you should shine a photon, or in other words, you shine the light or laser, and then inside the light there will be a photon which carries the amount of energy, and then that amount of energy will raise the energy level from a lower energy level. So yeah, it is a kind of a reverse process, even though when you learn about the um, hydrogen atom, what you generally learn is that the the energy level of the electron is actually being reduced. But opposite process is also possible because of the energy conservation law. And then in quantum information, we don't need to use all of these multiple energy level. So we generally consider only the lowest two energy levels, and then we call such kind of model as a two level atom, or TLA. And then so we basically ignore all these other levels, and then we can just assume that the electron can either sit in this lower energy level or this higher energy level. And then in this case, we generally have the name for each of the level, because the lowest energy level is generally called as a ground state, so it will be represented by G, or the higher energy level is called as excited state, so it will be labeled with E. However, in the quantum information situation, we generally prefer to use either 0 or 1. So we just label each of the energy level as 0 and 1. And the point is that when we consider this kind of situation, then we know that the electron can either sit at the 0 state or 1 state. However, I mentioned that in quantum mechanics, the quantum state of the some object is actually represented by the vector in a Hilbert space. And then in this Hilbert in the Hilbert space corresponding to the two level atom, then we know that there should be some zero state, a zero vector, and then one vector. And then if the electron is in the zero state, then that means that the quantum state of the electron is represented by this this vector. And then if the electron is in the upper state or excited state, then the corresponding vector in the Hilbert space will be represented by this one. However, the most important point is that as I mentioned, the quantum state of the some object is not only aligned to the basis vector, but it can be represented by some arbitrary vector in the Hilbert space. So it can be something like this one. And then what does this mean in terms of electron? So that's a little bit weird situation. And then we know that any arbitrary vector in this Hilbert space can be represented as the linear combination of these two basis vector. And then you probably understand that you probably have no problem in imagining the situation when the electron is sitting either in 0 or 1 state. But what does this mean? So to answer this question, we have to use the third postulate. But before we do that, I can also mention that if we start with the ground state, then by shining some laser which corresponds to the energy difference between these two energy level, then if this photon carries enough energy or exact energy corresponding to this energy difference, then and as we shine the laser, it is not like when we shine the laser, it will immediately go up, but the probability of being in the excited state will start to increase in time. And if we shine enough laser, then if I represent in terms of this vector, then initially uh, uh, when the electron is in the ground state, then it will be represented like this one. And then if we continue to shine the laser, then the quantum state will keep changing like this one. And at some point, it will be equal to the one state, which means that the electron will be definitely in the excited state. However, if we keep shining the laser, then it will also start to decrease like this one. So at some point, it actually goes back to the zero state. So that's what happens inside the atom. We can also think about another model, another quantum state model, which is the polarization. I assume that you are familiar with the concept of the polarization of the light, but let me give you some review of what you know so that I can continue my discussion for the quantum state of the polarization. Um, you know that when the electromagnetic wave propagates through the either vacuum or some medium, then electric field is oscillating along some axis. And then this is one of the popular picture for the um, polarization when the electromagnetic wave is propagating from one direction to another. And then the most familiar example of the electromagnetic wave is probably the wireless communication. So your smartphone is connected to the internet through the cellular network or um, through the Wi-Fi network. And then for both cases, it is using the electromagnetic wave. On the other hand, um, you are familiar, and then yeah, whenever you see the propagation of electromagnetic wave, then yeah, you would have seen this kind of propagation picture, and then this one actually describes the polarization of the light as well. And then the main difference between the wireless network, um, wireless communication, and the light is the frequency. So typical electromagnetic wave is the wireless communication generally use the frequency of order of maybe several hundreds kilohertz to several tens of gigahertz nowadays. Yeah. While for the case of the light, the frequency range is for the visible light, the frequency range is order of 400 terahertz to 800 terahertz. Yeah, of course, there are even higher frequency or lower frequency, but you generally cannot see them as a light. So except these big frequency difference, electromagnetic wave you are using for your wireless communication or the light, there is no difference. So I can explain the polarization either in terms of the electromagnetic wave propagation or the light. But actually, to explain the polarization, um, electromagnetic wave is easier to explain. So yeah, let me use the example of this electromagnetic wave. And as I mentioned, yeah, you should realize that when the electromagnetic wave propagates, then it has a direction of the propagation. And then here I assume that it is propagating along z direction, z axis. On the other hand, the electric field is actually oscillating along the axis, which is orthogonal to the direction of the propagation. So for this case, the electric field is I just drew a picture. I just picked one of the case in such that the electric field is oscillating along the x-axis, but there is no reason why it should only oscillate along the x-axis. And then still, yes, I assume that some of you are still not familiar with the concept of the electric field oscillation while it is propagating along some z direction. So yeah, let me give you some more simpler example for the um, electric field. So instead of considering about the oscillating case, yeah, let me start with the case for the static electric field. So you are familiar with the concept that if you have some charge, then from this charge, you would have some kind of electric field coming out, emitting from this single point. And then how did we find out this field? Well, the way we find out this one is that by putting some test charge here. Yeah, so maybe I can say that it is a plus charge, and then if I put the plus charge, then this plus charge will receive some force, and then all the electric field line means that whenever I put the um, charge here, then the force is pointing in this direction, while when I put the charge here, then repulsion or the electric force is pointing this direction. So these electric field simply are the just connecting all the force direction along within this space. So that's the definition of the electric field. And then I also want to point out that electric field behaves like a vector. And then as you are familiar with, as you know, for this case, if I have a plus and minus charge, then we know that the electric field is formed like this one. But then why, why we would have this kind of behavior? Well, the simple answer is that if we put some test charge here, then this charge will receive the force from this plus charge. So in this case, it will receive this direction. On the other hand, this one is negative, and this one now will pull this this charge towards to the this negative charge. So the amount of force applied by this negative charge is along this direction, and then um, this is the force and this is the force, and we know that the behaves like a vector. So yeah, in this case, we can just add these force together, and then we know that at this point, the direction of the electric field is not this direction, but it should along this direction. So that's how we found out these fields. And then from this fact that the electric field is simply a representation of the force. So the algebra for the electric field should also follow the algebra of the forces. And then we know that forces basically all the force calculation is based on the vector calculation. So yeah, electric field also should have the behavior of the should also follow the algebra of the vectors. And then now, if I go back to the polarization, I mentioned that polarization is also the electric field. So how can we find out this kind of picture. Well, yeah, just assume that we have some propagation of some electromagnetic waves, and then we just freeze the time, and then at some fixed time, we we are just assuming that we can fix the time at some point, and then to find out each of these arrow, what we should do is put the test charge at this point, and then find out that it is receiving some force along to the positive x. Again, if I put some test charge here, then it is receiving this direction, the force in this direction. And if I put the test charge here, then there is no force. And if I put the test charge here, then this charge will receive the force along this direction, and so forth. So these arrows are just a representation of the direction of the force when you put the test charge along this axis. So yeah, again, the um, the polarization is basically the electric field, and then electric field is following the vector algebra. So all the discussion of the polarization can also be described in terms of the vector algebra. And then where so in the daily life, when uh, when did you see the application of the polarization? I think yeah, these days 3D TV is no more not popular anymore. But if you think about 5 years ago or 10 years ago, yeah, 3D TV was very popular. And then at the time, yeah, people should use the should wear the some glasses, and then yeah, depending on the technology, some of the technology use the polarized glasses. So yeah, well, actually, yeah, if I uh, give some more details, then typically the Samsung TV was using a little bit different way. So they were using the shutter, active shutter for different eyes, but but LG generally used this passive way to distinguish two images for each of the eye, and then um, even if we are looking at the same screen, if the image intended for the left eye has different polarization compared to the image for the right eye, then even if we are looking at the same screen, um, in principle, we should be able to see different images with different eyes, and then that's how you can feel the 3D effect um, for using these polarized glasses. Then why am I interested in the polarization? That's because polarization actually has the very similar property to the quantum mechanical situation, and then where actually the description of the polarization can be is equal to the description of the quantum mechanical situation, and then also um, polarization can be also related to the digital communication. Let's say that we want to do some digital communication, not the quantum mechanical based communication, but using the polarization. One option is that we can define so when we want to transmit zero information, then we decide that we will transmit the horizontally polarized polarization, meaning that the polarization will oscillate along this horizontal direction, while when we want to transmit the information of digital information of one, then we will transmit the um, photon whose polarization is aligned along vertical direction. Then, yeah, for example, if the even if the starting line has some arbitrary polarization, after it is transmitted through the polarizer, then it will be horizontally polarized. So yeah, the sender wants to send the zero information, and then the receiver, depending on which orientation this polarizer is oriented, then for this case, this horizontally polarized light cannot be transmitted through this polarizer, and then the receiver can know that, oh yeah, the because the receiver won't measure any of the transmitted light, so the receiver can conclude that the transmitted polarization is along the horizontal direction. So this sounds very good for the digital communication, but is that all we can do with the polarization? No, because um, there is something which can happen with the with the polarization, but that cannot be explained in terms of the digital communication. For example, if I insert this kind of polarizer which is tilted by 45 degrees, then suddenly the yeah, this one will corresponds to the measurement, but only by having additional measurement step between the transmitter and the receiver, then the transmitted information will be changed. Yes, and then it can be explained easily by considering this situation, because when the when this horizontally polarized light is to determine how what will happen to the horizontally polarized light when it is passing through the 45-degree tilted polarizer, then to interpret this situation, we have to decompose this vector component into two components. So you know that this this vector can be decomposed into these this vector component can be decomposed into the sum of these two components. So yeah, that's why I wrote down here. Then this component is orthogonal to this grating, or this kind of pattern. So it will be blocked, and only this component will be transmitted. And once it is transmitted, then now yeah, it will meet this polarizer, and then to determine what will happen, then we have to now decompose this one into this type of two polarization. Then we also know that this can be also decomposed into two components like this. Yeah, so like this, and then we know that this component won't be transmitted, so only this one will pass through this polarizer, and then we will obtain this one. And then if from the perspective of the receiver just measure the non-zero light, and then from the perspective of the receiver should interpret this situation as one because receiver will strongly believe that if the transmitted light was zero, then there should be no transmission. So yeah, this is completely counterintuitive in the during the for the case of the classical communication, because in the classical communication, if we transmitted digital information zero, then even if there is any kind of measurement in the middle, the final transmitted information cannot be changed. But here, just by measuring, yeah, we can affect the transmitted state. And then, yeah, of course, it is not. Yeah, we should be a little bit careful, because yeah, when it is if the starting light has the intensity of 100, then we know that only half of them will be transmitted, and then this half will be also only half of this half will be transmitted through here. So only the quarter of the original intensity will be transmitted. However, what I want to point out here is that the transmission of the quantum state or polarization state is requires different types of analysis compared to the typical digital communication. And then for to understand the polarization more carefully, we need some more careful analysis, because this kind of analysis is a little bit inaccurate. And then yeah so in the next page I will do more rigorous description. But before I do that, let me also give you some show you some simple experimental demonstration for this situation. The first demonstration I want to show you is that the light, laser light coming from the pointer is polarized. So this is just a typical laser pointer. And then if I if I put the then you can see that the amount of the light is slightly attenuated. But the more important part is if I rotate this one, then the intensity is being changed. So for this case, the transmission is maximized along this axis. As I rotate this one, then the transmitted intensity is reduced. And then again, if I rotate in this way, then it is increased again. So from this one, you can see that the laser light is polarized. Another demonstration is that when the orthogonal, so these are the two polarized light. And for this case, if they are just separated like this one, then there is no problem in the transmission. And then if I just overlap the two polarizers, two polarizers on top of each other, then there is no problem. But if I just turn this one orthogonal to each other, then the transmission is completely blocked. So this is exactly what I just showed you in the previous slide. And then again, even in this case, I can still make the transmission again, and then it can be demonstrated by inserting this kind of 45-degree transmission. So for here, we know that it is completely blocked, like here. But even in this case, if I just plug in, if I insert the insert the additional polarizer between them, then the light is being transmitted, depending on whether I insert this one or not. So this is so as you can see here, that this basically shows that um, the interpretation of the polarized light requires more than just the interpretation of the digital situation. In the previous page, I mentioned that the current description of the polarization was not accurate enough. So let me explain the problem, and then let's see what will be the correct way to describe the polarization. In the previous page, when I described the decomposition of the horizontal polarization, then I said that this can be probably a summation of these two smaller vector components. But this one, depending on how you view this situation, for the current case, I first added this one and then later add this one. Then the summation of this one will make this the total of this size. But another option is I can add this one first and then do the summation of this one later. then the summation of this one corresponds to the vector of this one. So there is some issue with current representation, and the problem is, even though the polarization is oscillating in both directions, we should define some kind of concept of the phase. And then, yeah, let's begin with the such kind of description. So the first thing is that, yeah, yeah, we are currently we are comfortable with the concept of the horizontal um, horizontally polarized light, and then vertically polarized case, yeah, like this one. Then the next thing we can think about is um, what is the polarization which is oscillating along, yeah, along the this diagonal direction. Yeah, so the polarization, depending on the time, the polarization might pointing in this direction, and at another time it will be pointing on opposite direction, and it is keep oscillating along this way. And for that case, we will, yeah, represent this kind of polarization as a diagonal polarization, and it will be generally represented as the summation of the horizontally polarized plus vertically polarized light. And then, yeah, we need this kind of normalization factor, but yeah, it can be, yeah, I can explain why we need this kind of normalization factor in the when we are discussing about the third postulate. And another possibility for the diagonal polarization is that instead of um, oscillating along this axis, there is another component which can also oscillate along this axis. And for that case, if I want to have a if I want to have a polarization which is oscillating along here, then I will call this this vector as anti-diagonal. And then for this case, yeah, you can see that if you just look at the um, uh, if you just consider this vector as the combination of these two vectors, then yeah, we can just write this one as this kind of linear combination. So yeah, this sounds reasonable, but there is more we need to talk. We need to consider, because for this case, I added minus in front of the horizontally polarized case. But what do I mean by minus sign or plus sign, or more generally, uh, yeah, I will call this one as the phase. And the problem is, we know that horizontally polarized light is oscillating along the horizontal direction. So whether it is pointing in this direction or opposite direction, does that really matter or not? Yeah, so that might be confusing. And the answer is that depends on where does the this sign appears. If this sign appears at the global level, meaning that the same minus sign is multiplied on both term, then we call it as a global phase. And then such kind of global phase doesn't matter. But if we only add this kind of phase only in front of the one of the component, or only a subset of the component, then yeah, those phase really matters. So yeah, let's see why. Yeah, let's try to interpret such kind of situation in terms of the wave. Yeah, so when we are modeling the wave mathematically, then we have to consider this kind of concept. Yeah, so um, yeah, we have some wave like this, and then yeah, let me just draw one period of the phase. Yeah, well, a little bit more. Like here. Yeah, and then yeah, how yeah, and yeah, this sinusoidal curve can be simply represented as a cosine over and then we call this length as the wavelength, and then I will represent the wavelength using the lambda, and then to describe this kind of case, then as the z variable changes from 0 to lambda, then the phase inside the cosine should be changed by 2 pi. So we can just by uh, representing just writing it this way, then the this curve can be described in terms of the um, um, mathematics, and then yeah, we instead of dealing with the cosine or a sine function, we generally prefer to use the Euler relation. So we know that this is the same as the just taking the real part of this kind of summation plus I and sine 2 pi over lambda z. And then, we know that this one can be replaced by exponential I 2 pi over lambda times z. So, in and then, because we are only interested in the real part, the this expression and the next expression are equivalent, but you will realize that this kind of notation is much easier to deal with compared to this one. So we want to continue to use this Euler relation. Like this one. And then let's consider a little bit different case. So we have the same size of the axis with the above one, but assume that this wave is shifted by one lambda over 8 amount. Meaning that this one is slightly shifted, and then it is something like this. So and then this amount the amount of shift is only lambda over 8. Then this curve can be also described by in terms of the cosine, and then in this case it is shifted by lambda over 8. So to the right to the left. So we have to add lambda over 8 like this, and then this corresponds to the and then this one. Oh, and then I also forgot to mention that um, when we are describing about the wave, then instead of using 2 pi over lambda, which looks complicated, we generally redefine this factor as the k, and then we call this this value as the wave number. So instead of writing that one, I will just replace this one by kz. And for this case, this is again k. So this equation can be turned into kz plus, and if it is multiplied together, then lambda will be cancelled with each other, and then 2 will cancel the 8, and then it will become 4. So it will be lambda pi over 4 phase. And once we have this one, then we can rewrite this one in terms of the Euler relation. So it is I kz plus pi over 4. Or this can be also represented by exponential I kz times e to the I pi over 4. Yeah, something like this one. So now this pi over 4 came from the amount of this shift, and then for this minus sign can be also interpreted as the exponential I pi. So this minus sign actually means that this wave is shifted by lambda over 2 amount. Yeah, so half of the half of the wavelength. So then how is this related to the propagation of the or direction of the polarization? Well, yeah, if we consider this combination in terms of this wave, then the situation might be more intuitive. Yeah, so to represent the um, um, diagonal. Oh, and I also forgot to mention that yeah, typically, yeah, if we want to represent this vertically polarized light, the more complete expression should be that it is yeah, if I call this axis as z, and if I call this axis as x and then y, then the polarization is polarized along the x-axis. So we should have something. Yeah. So for this kind of wave, then it should be either used written using the cosine or a sine. Yeah, and then for the simplicity, let's use the cosine. Yeah, even though yeah, I didn't necessarily specify that this is a 0 point. So if I just call this one as a 0, then yeah, I can use the cosine without any problem. So for this case, yeah, this will be probably the correct description of the this oscillating field for the electric field. However, instead of trying to use this expression, we generally prefer to use the Euler relation type. So yeah, I will use exponential I k z, and then yeah, I will also include the unit vector for the direction in the 3D three-dimensional space. However, and then and if we have some kind of additional phase like plus phi, then I will also include that one to here, so that it will be something like phi and the direction of the polar oscillating direction of the oscillation. So this simply means that it is oscillating along the x-axis, and then yeah, yeah. So this is a correct description of this kind of field. However, we will realize that this real part, real symbol, and then this exponential e to the I kz will appear for all the wave. So it is kind of redundant, or yeah, all the analysis can be done by using only this part, and then once all the calculation is done, then we can just multiply this part later, and then take the only the real part of the entire expression. So yeah, instead of dealing with the complicated expression, we will only use this part to represent our polarization. So that's why we can have this simple expression rather than all these complicated cosine or sine or exponential e to the I k z to here. So yeah, whenever you see this expression, then you should you should not forget that this expression implies that these parts are temporarily omitted. But later, when you need to you need to analyze in full, you need a complete analysis, then you have to multiply this one back, and then you also take the real part. So yeah, considering such kind of situation, then this diagonal polarization can be understood in this way. So now I'm just defining that the x-axis corresponds to v vertical vertical polarization direction, and then y-axis corresponds to the horizontally polarized direction. Then the summation of these two components means that yes, so this one corresponds to here what I'm drawing is the field along along y-axis, and then this one will also have this kind of component. Yeah, something like this one. And then if we look at the and then because the polarization is behaves like a vector, so at each of the point, the polarization is determined by the summation of these two vectors. And if we look at the problem from this side, then it corresponds to the the coordinate system showing for like this one. And then if I look at from this direction, then for this location, the summation of the two vector will look like it is summation of this one. So yeah, it is polarized like this one, and then it is the summation of this this and this vector. Yeah, so it is polarized along this direction, and then this direction is represented by this d vector. And then when the when this half period is passed, then later, now the all the direction of the oscillation is reversed. So the vertical along the vertical direction, the field is pointing down. So it is pointing down, and then the this field is pointing in the negative direction to this way. So now the summation of these two fields, these two polarization vector point into this direction. So eventually the oscillating field is oscillating along this direction. So that's how is the diagonal direction, diagonal polarization is defined. Then what about the anti-diagonal? Yeah, for this case, let me just erase. Yeah, for this case, it is opposite case, because now now the sign of this one is negative, and then we know that negative sign means that the so this sign corresponds to the phase, and then pi phase means that this wave is shifted by half of the lambda. So what that means is that previously the wave was like this one, then now this entire wave is shifted by half of the lambda. So now the this one goes to here, so it will look like this one, and then the following part will also appear along here. So it will be something like this. And then sorry, that here. but it is oscillating like this way. And again, if we look at from this direction towards to the plus z direction, then now all the vertical direction, yeah, or around this area, the vertical component is pointing in this direction, while the horizontal component is pointing negative direction, which is over here. So the summation is pointing in this direction. So around this area, the polarization is along this direction, and then after half of the period, then all the signs are reversed. So now the vertical component is pointing down, and then horizontal component is pointing along this to the right. So some of these two direction is pointing now in along this direction. So this means that the polarization is oscillating along this axis, and it goes into this direction and then backward and so forth. So it is oscillating along here. So now, yeah, you may by now, yeah, the notation of this makes more sense compared to when you saw this notation for the first time. And then, yeah, of course, this by itself cannot give you insight. So yeah, whenever you try to understand what happened, then you have to imagine this kind of situation. So this summarizes the polarization state of the light, and then yeah, I just described that two frequently used notation, which is called as diagonal and anti-diagonal. And then for this case, in this case, I multiply the negative sign in front of the v, and then as I mentioned before, the global phase actually doesn't matter. So yeah, whether we multiply minus sign in front of here. Yeah, so yeah, in front of here. So yeah, you can just imagine that this is another way to um, represent the anti-diagonal direction. And then yeah, these other cases are also interesting. And then if you are curious, then you can also explain why these are um, 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 if you calculate, if you follow the analysis I just showed you before, then you will also realize that the um, polarizations are rotating in time. Yeah, so and then I will skip the explanation for this one. So up to now, yeah, all of my description was that it was based on the wave argument. So you might get the impression that the light is a wave, but you also know that light also behaves like a single particle, which is called as a photon. So and then yeah, there were also a lot of evidence that the light is yeah, and so yeah, the concept of the photon is that we believe that the light is well, when we shine the laser, then the laser is propagating continuously. But yeah, even though it looks like continuous, yeah, in if we really look carefully, then the energy is bunched, and then yeah, each of these particles are flying simultaneously, or yeah, one by one, and then we call such kind of a particle of the light as the photon. And then what is the evidence for the photon? Yeah, why do we believe that the energy is discretized? And then there are several evidences, and then yeah, the most famous one are probably these three. The first one is called as black body radiation. And black body radiation means that when you increase the temperature of the metal, then you generally see that the color of the metal is changed to the some a red color, and um, um, such kind of behavior could be generally explained by using the electromagnetism. But there was some problem. People could derive some relation at the low temperature and then high temperature, but they could not have a universal formula for the blackbody radiation. And then the problem was people were always to calculate based on the argument of the electromagnetism. People were always integrating the situation, assuming that the energies are continuous. But these results never satisfy the entire range of the spectrum. But yeah, Planck somehow thought that instead of just doing the integration, if we assume that the energies are discretized, and then if we sum up all those energies, then yeah, he realized that this kind of summation result actually can perfectly explain what was observed experimentally. So, but even if he just assumed that this integration should be replaced by the summation, but he never expected that the energy should be discretized. However, you also know about the photoelectric effect, and then this was properly explained by Einstein, and then photoelectric effect was the following. So if we have some metal electrode, and then assume that we apply um, uh, yeah, and maybe we can also assume that there is another electrode, and then we apply we ground it. Sorry. Yeah, so this metal is grounded, and then we apply some positive voltage. Yeah, so maybe I can just draw this way. Yeah, so positive and negative connected to the ground, and then this one. Yeah, so that means that the electric field is pointing in this direction. And for this case, um, people started to shine the light on this metal, and then people realized that at some point, uh, the the electron inside this metal part started to come out. But the condition for um, pulling the electron out of this metal was a little bit weird, because in some case, even if people increase the energy of the light, the the electron didn't come out. But even with a very small amount of energy, sometimes the electron came out, and the criteria was not the absolute energy, but the frequency of the light. So yeah, people realize that when the frequency of the light is larger than some threshold, then the electron started to come out, and then it was pulled to the other end due to the electric field, and then in that case they could measure some current here, and then until the frequency of the light goes above some threshold, the electron didn't come out. So yeah, that was the one of the puzzle, and then yeah, such kind of phenomenon was properly explained by Einstein, because what Einstein assumed was that the each of the photon carries the amount of energy which can be quantified by quantified by h times nu, and then here nu means the yeah, let me just use the f. Yeah, so h times the frequency, and then this h value is something called as Planck constant, and then it has this value. Actually, this one, this value is when we divide it the h value by the 2 pi. Yeah, so and then for this case, we call this value as a haba, which I mentioned in the previous lecture. And then yeah, what people realized was what Einstein realized was that only when this value is above some threshold, then the electron comes out. And then the explanation was the following. So yeah, assume that for the electron to come out from the metal, then there was some amount, a minimum amount of energy, and then the electron was sitting at some other energy level, and there is no intermediate energy level. So only when the um, electron receives enough energy, then it goes above this threshold, and then it can come out of the metal, and then it can freely fly to the other side. But until the electron receives enough energy, it could not escape. And the problem is the energy was carried by each photon. And then if the uh, energy carried by the photon was not enough to overcome this threshold, then because there is no intermediate state, so it cannot go to here and then obtain another photon, but it should at least get more than this threshold energy. So what that's the effect of the this photoelectric effect. And finally, the Compton effect was the following. So Compton effect means that the electron was here and electron was flying away. And then if we send out some light, then um, this electron, the scattering of this electron, meaning that it will change its direction and the energy, and then this angle was always constant if the condition for this one was the same. So and then so the electron will follow the energy conservation law and then momentum conservation law, and then to uh, to satisfy the those laws, then um, then people could calculate what is the required value for the energy of the photon and then momentum of the photon, and then such kind of calculation all agreed with the result from these other cases. So for these three completely different experiment, they use the same constant, same Planck constant. So people could be convinced that the energy of the photon, energy of the light should be quantized, and then we call such kind of quantized energy as a photon. So yeah, this one somehow summarizes the first postulate. So I spent a lot of time on the first postulate, but I hope that you can get some sense of what is going on with the quantum mechanics. So let's move on to the second postulate. As we discussed about the second postulate in the previous lecture, the second postulate says that the change of the quantum system or evolution of the quantum system is described by a unitary transformation. And then I will at this point probably closed means close may mean nothing to you, and then you will realize what does this mean later. And then for the time being, you can just ignore this part and then assume that the evolution of the quantum system is described by the unitary transformation. And then I mentioned that this means that over the time, the initial state might this one, and then final state will be different vector in the Hilbert space, and then those two Hilbert space, those two vectors in the same Hilbert space can be connected only through the unitary transformation. If the quantum mechanics is applied. And let's consider some of the example. Yeah, we discussed about the X operator, and then for this case, if we multiply this matrix on this zero vector, then we know that it will turn into the one vector, and the vice versa. So this gate behaves very similar to the NOT gate in the digital circuit. And then what about another unitary transformation? And we call this one as a Z gate compared to X gate. And then the role of this one is a little bit embarrassing, because if I multiply this Z gate on this vector, then you will realize that it will be just the same vector like this one. But if we multiply this one on the one state, then you will also realize that the final result is 0 and -1. So that means that it is the negative of the 1, and then you will obtain this situation. So Z gate does not have any corresponding concept in the digital logic. So it is well known that the quantum computer can, in principle, implement all the digital gate in the digital logic, but there is more than the digital more other types of gate, such as the Z gate, and then there is no concept of the phase in the digital logic. So and then you will realize that this kind of concept is very useful in design of the quantum algorithm. And another popular gate is called as Hadamard gate, and Hadamard gate looks like this one. And then if you multiply this Hadamard gate on 0, for example, if I multiply 1, 1, 1, -1 on the 1, 0, then that means that we will have 1 over square root of 2, and then this is 1 and this is 1. So what this means is that this 1, 1 is the summation of two vectors, 1, 0 plus 0, 1, which is 0 and 1 basis vector. So yeah, even if we started with the well-defined value of 0, the final result is actually the superposed or the linear combination of these two basis vector. And then similarly, if we apply the Hadamard gate on the one state, then you will obtain this another types of the linear combination of these two vectors. And then if you remember about that polarization case, then we might consider this is one 0 corresponds to horizontal and then 1 corresponds to vertical. Then in this case, horizontal polarization is turned into the diagonal polarization, and then vertical polarization is turned into the anti-diagonal polarization. And such kind of change can be actually implemented very easily, because in optics, if we have some light coming in here, then there is something called as halfway plate. And then depending on the angle of this halfway plate, you can either implement this is some kind of crystal, and then we can rotate the axis of the crystal, and depending on how is the axis of crystal aligned, sometimes it can implement completely this kind of situation, or even this Hadamard gate can be easily implemented. And another version of the second postulate, it was the continuous version. And then for that case, what it says was that the evolution of the quantum state, or the vector in the Hilbert space, is described by something called as a Schrödinger equation. And then Schrödinger equation looks like this one. And then here, Haber is the same Planck constant which I mentioned in the previous page. And then this H script is called as a Hamiltonian. And then what we generally say is the Hamiltonian describes how the system evolve. And then probably this kind of equation still does not make sense to many of you. So yeah, let me just give you some physical meaning of this equation. One thing I should point out is that this Hamiltonian should be Hermitian, because in the previous lecture we saw that this equation can be turned into this shape, and then if the solution for this kind of differential equation will be like this one. And then if this operator is Hermitian, then we know that well, I didn't prove, but I asked you to prove that this exponential function will always become the unitary operator. So yeah, and then we know that from the postulate 2, the connection, the quantum state at time t equals so at some time t should be connected to the previous quantum state through the unitary operator. So to make sure that this operator become unitary, then we need to have a Hermitian operator at the position of the Hamiltonian. So this part is a kind of requirement for the Hamiltonian. And then another concept I want to explain here is that the Hamiltonian corresponds to the total energy. And then yeah, at this point I cannot prove that the Hamiltonian is Y total energy, but at least if you accept that the Hamiltonian corresponds to total energy, then this equation might make more sense, because in previously I mentioned that the wave of the electromagnetic field generally can be described by the exponential function like kz. And then here, yeah, I was not yeah, when I just had only this shape, then this wave is kind of stationary over the time, meaning that the shape of the this sinusoidal curve does not move even if time is changed. So if you want to describe the wave which is propagating in time, then you also need additional factor like I kz minus omega t, or something like this one. And then yeah, if you have this one, then it is actually properly moving in time. And then this shape is actually related to here, because if I apply these factor apply the time derivative to here, then we know that the differentiation of this one will become yeah, this time will work on only this one. So I will have minus I omega multiplied by I kz minus omega t. And then this exponential part still is similar to this vector in the Hilbert space. And then the calculation of this one only brings the some part of the exponent, but then we have to multiply. If we multiply IH bar like here, then that means that I also have to multiply IH bar here, and then multiplication of I to minus I will become plus 1. So I can erase this part, and then it will be multiplied by Habar, and then we have this Habar times omega. And then what does this mean? This means that the Habar is defined as h over 2 pi, and then omega is defined as 2 pi f. So the multiplication of this Habar omega means that yeah, because the 2 pi will be cancelled with each other, so it is HF. And then what was the HF? It was the energy carried by a single photon. So the the left hand side actually um, shows another way to obtain the uh, total energy information for the photon case. And then this kind of wave function is not necessarily limited to the photon, but all the electron quantum state is also has form similar to this one. So the this left hand side somehow has the meaning of the total energy carried by some particle. And then I mentioned that this Hamiltonian also is generally derived based on the classical total energy. So yeah, all the Schrödinger equation means that is the energy is the same as the energy. So at least that makes sense in terms of the meaning of the equation. So yeah, and I know that this kind of explanation is not complete, and then yeah, probably many of the students are still confused by the Schrödinger equation. And then yeah, the good news is that in this class we won't solve any of the Schrödinger equation. So yeah, the only reason I'm just including this one is for completeness. So if you don't understand the Schrödinger equation, then you don't have to worry about the situation. Yeah, because all you have to understand is that the fact that the quantum state can be only evolved, yeah, through the unitary operation, yeah, unitary transformation. Okay, so for today I will stop here, and then we'll continue in the next lecture.